Okay, so before the examples, as I promised you before, I'm going to, I'd like to talk about notation. So how do we on paper denote the operation that we just constructed together? Well, first we should probably write out the result that we derived. So we derived that if we have a function f equals f of x, then the corresponding gradient function is equal to the limit as delta x tends to naught of f of x plus delta x minus f of x naught all over delta x, and this is evaluated at some point x naught. Now, we said before that this is called the derivative of f of x, and well, we said here, but I'll say it a third time, this is actually the gradient of this function f of x. It will become more concrete with more examples, but this isn't really a very useful notation. We have to explicitly write out gradient function equals the some limit. So the most conventional notation is to say for the function f equals f of x, we define df by dx equals the limit as delta x tends to naught of f of x plus delta x. Now notice I've used x instead of x naught. That's just the justification you can use for that is simply to save pen, if nothing else. But it's not really very conventional to talk about some point x naught. We say some point along the x-axis, and we denote that by the letter x. So x naught was kind of like just for demonstration purposes when I drew out a diagram, but just so that we wouldn't really confuse it with the label on the axis. Now we say the limit is delta x tends to naught of f of x plus delta x minus f of x, all divided by delta x. Now we also remember we called this quantity here, we called this quantity here in the first video, or the last video, we called this delta y by delta x. Now that sort of gives us a justification for this notation, because we can consider this as if it were some kind of infinitely small, or the word we use in mathematics is infinitesimal, change in f of x. So infinitesimal means infinitely small. So some infinitely small change in f of x divided by some infinitesimal change in x. So this is kind of like the gradient, but all we're doing is we're taking the limit of the gradient as we approach that point. Between two, we started with 2 points, and we make the second point approach the first by taking the limit as delta x tends to naught until we have an exact gradient. We denote that by df dx. Now this is just a notation, so we're not actually saying some quantity df divided by dx. So please don't ever try to do this. Don't try to cancel the d's, because that doesn't actually mean anything. That's very, very, very wrong. And I'll show you why in a minute. So I'm going to just as a little note just to write here, the most conventional notation for the derivative of f of x. Now, other notations that are frequently used are to say, well, we can think of this kind of like a different, this thing as kind of an operator that has operated on f to give us the gradient function. So, another notation. So we'll start by we'll just list them all off. So we'll start by saying our notation we said here, df by dx. We'll put a little note next to that. Conventional. Another notation that's frequently used is to sort of think of this like we're operating on f of x. So we would say dx of f of x. So we sort of like let the f slip down and say we are operating on it. So we'll call this our operational notation. So it's like we're operating on it. So we're going to operate underline the operat bit, so we know it's so it's not like, I know you don't get confused in the future, it's just we're operating on it. So the final notation that's commonly used is to say if we have f equals a function of x, then we would say f prime of x. Now, right here, prime. Sorry, that's a very, very bad handwriting. Prime. And this is actually a notation that was introduced by Isaac Newton, so it's called Newton's primed notation. So if we have a function f of x, f prime of x denotes its derivative, and it's a useful way to write it down on paper. And of course all these notations are exactly equivalent. They mean exactly the same thing. So now that we've done that, it's probably a wise idea to move on to some examples. So the first example I'd like to give you comes from from our last video. So let's go right here, examples. The first example is the problem. Say we have a function f of x equals mx plus c. Find df by dx. Now, we kind of already in our heads know what this will be, because remember, df dx is a gradient, right? So what we should find from this is that if we label this y, label this x, draw the line, draw the straight line, we say this is the graph f of x equals mx plus c. What we should find is, well, firstly that it crosses the y-axis at c, and that we have a little gradient here, so we label this delta y by delta x, that m is equal to delta y by delta x, which is of course the same as the gradient, so we'll write that as df by dx. And that is what we'll find, but I'm going to prove it by using the piece of calculus that we just derived for ourselves. So we'll start by, so if you remember before we said that df by dx is defined, that's what the three lines mean, defined as the limit as delta x tends to 0 of f of x plus delta x minus f of x, all divided by delta x. Now, f of x plus delta x, we get that simply by, in f of x, everywhere we see an x, we replace that with a delta x. So we have m times, instead of x, we replace that with x plus delta x, and then plus c, which is of course equal to, if we multiply out the brackets, mx plus m delta x, and not forgetting to add c. Now, this quantity here, remember, we call that delta y by delta x. So just to make this a little nicer, we'll start writing delta y by delta x is equal to f of x plus delta x, so mx plus m delta x plus c minus f of x, which we said before, in fact we wrote that was mx plus c, so we must subtract from this subtract from this mx plus c, so the entire object, this is subtracted from it. So we can see, and then, we must divide that by delta x. We can see here that we must cancel mx and the c's cancel, so what we're actually left with is m delta x divided by delta x. Now this is very simple because all we need to do is now cancel the m's, and I think you can sort of see where this is going, because now we can write that if f of x equals mx plus c, this implies that df by dx equals the limit as delta x tends to naught of, delta y by delta x, which is the same as m, which we've just derived, and, there are no delta x's here, so if we set delta x equal to naught, we will come out with just m. And I'm just going to put a little box around that because that's our answer. Which is of course what we expected, because that's what we got there, because it's characteristic of a straight line, that its gradient is the same, it's constant everywhere, and equal to m in the equation for a straight line, f of x equals mx plus c.